Great, we're going to get started. Welcome everyone to another talk at Chilloquium, hosted by the Harvard-Radcliffe Society of Physics students. My name is Andrew Vinitsky. I'm an undergraduate studying physics and mathematics here at Harvard, and I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderator, Minchell Park, and we're very honored and very excited to have someone we've wanted to have at Chilloquium since its very inception 2 years ago, Professor John Preskill from Caltech, speak with us today. As always, if you have questions at any time, you can raise your hand in the Zoom participant sidebar and we'll call on you, or you can privately send a message to me and I'll ask for you. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. If you've been with us before, you'll have heard this already many times, but in case you've never joined a Chilloquium before, the spirit of this is to be a very relaxed and personal conversation and to hear about Professor Preskill's background and his path through physics, as well as a little bit about his research. And it's a much more casual kind of colloquium, hence the name Chilloquium. We also request that everyone be muted unless they are speaking, and also have your video on if you are willing and able. Angel.
Oh, yes. Now let me introduce Professor John Preskill to the audience. Professor Preskill is Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology. He is also the director of the Institute of Quantum Information and Matter. After obtaining bachelor's degree in Princeton, he moved to Harvard for his PhD in high energy theory physics. And after his PhD, he was a junior fellow of the Harvard Society of Fellows. He joined Caltech in 1983 as professor, and Professor Preskill is now leading quantum information science and technology, very well known for introducing the important terminologies, including quantum supremacy and noisy intermediate scale quantum processor, and for proposing a lot of pioneering ideas, including GKP codes and the intersection between machine learning, quantum physics, and quantum advantage. Professor Preskill, please share your screen and start your talk. Thank you so much.
All right, well, thanks very much, Minchell and Andrew. I'm honored to be at the Chilloquium. This is going to be a very self-centered talk. As I understood the invitation, you wanted me to talk all about myself. So I found that to be irresistible. And so that's what I'm actually going to do. So if I misunderstood, this is going to be embarrassing for all of us. But anyway, you're going to hear a lot about me. I grew up in Illinois, in a Chicago suburb, Highland Park, Illinois, which unfortunately was much in the news this summer because of a tragic mass shooting on the 4th of July. But it was, a nice place to grow up, about 20 miles north of Chicago. I went to the public schools there, all the way through Highland Park High School. Nobody in my family had really a scientific background. Both my parents were trained as lawyers. My grandfather was kind of a hands-on tool guy because he owned and operated a hardware store. But I was always encouraged by my parents to follow whatever I was interested in. And the first thing I was passionate about was baseball. And I remember in particular following very closely the 1959 season. I was 6 years old. The Chicago White Sox were competing for the American League Championship, which they actually won, though they lost the World Series. And I chose Nellie Fox as a symbol of my interest in baseball because he arguably was the White Sox best player in 1959. He batted left-handed, like I do, though he threw right-handed. And he always had that plug of tobacco in his cheek, which was kind of his trademark. And what I already appreciated at about that age about baseball, which I found very fascinating, is that it's a very quantitative subject, that there are measures of player performance that one can follow. And there were the main ways in which you could find out what the statistics were for a player were in the newspaper, where you could read the box scores for every game the next day. And also on the weekend, they would give you the cumulative statistics of all the players. But there was another way. And back then, I don't know if this is so much the case now, a 6-year-old could by himself walk to town, go into the stationery store with a nickel in his pocket and buy a pack of baseball cards, which came with a piece of chewing, well, actually bubble gum. And on the back of these cards, although these are ones that are actually still hanging in my home office, on the back of these cards, though you can't see that here, were statistics, the lifetime statistics of the players. And so I became very interested in rating players and characterizing their performance. Now, it so happens that years later in the 1980s, there was kind of a revolution in our understanding of baseball statistics. And looking back, we were amazingly ignorant in the 60s about that. I mean, it seems pretty obvious when you say it, but the way to measure a player's value is how much do they help your team win games? And there are two sides to that. How many runs do they help you score, and how many runs do they help you prevent for the other team? And well, in the 1980s, associated with what people sometimes call Moneyball, one of my personal heroes, Bill James, was pivotal in this revolution. We understand baseball much better than we do now. So that's always stuck with me, that sometimes the experts don't really know, although eventually things get straightened out. Now, I had another passionate interest, which was ignited around that time, and that was in spaceflight, human spaceflight. It was the time of the so-called space race. And these are actual newspapers, which front pages that I saved and kept in a scrapbook, which I still have. So I snapped pictures of them yesterday with my cell phone. And I can remember the great excitement when Yuri Gagarin was the first man to orbit the Earth. And these two front pages are sort of bookends for human space flight in the 60s, from the first orbital flight to a landing on the moon. So this got me really interested in, well, how do rockets work? And so I started going to the library and reading about science. And that led to, well, you know, interest in, well, what's on other planets and what happens to stars. I learned about you know, red giants and white dwarfs, not about neutron stars and black holes. They weren't really a thing back then. And I got interested in electronics, and I used to put things together, you know, solder together radios, although I never understood how they worked back then. And I had a chemistry lab and all that. So I was pretty much obsessed with science growing up. And there's one book that I remember as being very influential. I bought it when I was 9 years old at the book fair, and it covered everything in science. And some parts I found really interesting, like probability and statistics and neuroscience. But what really struck a chord with me was the chapter on theoretical physics. Now, does anybody recognize the two guys in the picture? They were not actually identified in the book, unless you looked at the very fine print in the front notes. It's Feynman and Gell-Mann. And I didn't realize until many years later that this whole book was based on interviews that the author, James Werner Watson, did with Caltech faculty. Book came out in 1958. I bought it in 1962. And what really seems rather amazing is that when this book was published in 1958, it included, and it's a book for kids, an explanation of the discovery that parity is not conserved by the weak interactions, that physics looks different in the mirror than it does in real life. And that just blew me away and got me very interested in understanding fundamental physics. I mean, at the level that a 9-year-old understands it, which meant going to the public library and getting all these popular books about physics, most of which filled me with a lot of misinformation. But anyway, it was exciting to read about those things. So I led kind of a double life for a while because I went to every summer for 8 weeks in northern Wisconsin, and there tennis and basketball and track, and which I loved. And at the summer camp, it was a small enough pond so I could feel like I was one of the best athletes. But then during the school year, when I came home, it was a much, bigger community. And by the time I was 13 or 14, I wasn't good enough to play on the starting team in anything. But I discovered there was another way that I could excel in academics, and in particular in science and math. And by the time I was maybe 15 or so, I decided math was the coolest thing. And the thing that I loved the most was Gödel's theorem. The idea that there are things that are true, but which you can't prove. I thought that was the deepest insight the human mind had ever achieved. And that made me think I wanted to study mathematics. And somehow I got the idea, I'm not sure exactly how, that if you're going to do math, you got to go to Princeton, because that's where the world's great mathematicians are. Maybe it was because Einstein had been there, or so I thought. Anyway, that's what I did. I went to Princeton, and I intended to be a math major. I talked my way into a graduate level class on set theory and logic my freshman year, which, I enjoyed and I did well. But by that time, there were people who really were mathematically talented among my acquaintances, people I had met at Princeton, and I realized I was not like them. I, was not going to be a great mathematician. I just didn't have that ability. But also freshman year, I started to get excited about physics again. And, there were some great teachers who were pivotal there. One was Val Fitch, who taught electricity and magnetism. He later won the Nobel Prize for discovering the CP violation in the neutral kaon system. And John Wheeler was a very inspirational figure. He taught a whole year course when I was a sophomore, which covered everything in physics. He seemed impossibly old at the time. I mean, he had worked with Niels Bohr in the 30s on nuclear fission. How could he still be around? But he was 61 then, which doesn't seem quite so old to me now. But he had an unusual style as a lecturer. For one thing, he was very facile with the chalk and could make beautiful drawings. But he also had unusual ideas about how to teach physics to sophomores. He was finishing at that time his book on general relativity with Misner and Thorne, and so he gave us galleys, pages of the book to read. That's where I learned the differential forms, which I was learning about in math class, had something to do with physics, and were useful for understanding geometry and space-time. One of the things I never forgot is the very first lecture of the year. We're going to learn classical mechanics. We've got this book, Goldstein Classical Mechanics. I'm excited. We're going to learn about Lagrangians and Hamiltonians. And the first lecture, and very apropos of the picture here in the upper left of the slide, he came in and he drew, A and B, and he said, there's an electron. It starts at A, it's going to wind up at B, but how does it know how to go? Which path should it take? He said, well, it takes all the paths, of course. It follows them all, and then it adds together all of their phases with an E to the IS, and all of those phases add up along this line. And he was about to tell us about the variational principle for classical mechanics, and he thought it was important for us to know where it came from, that there was a deeper explanation in terms of quantum physics, which his student Richard Feynman had discovered. So that was not the first time that he surprised us with his approach to explaining new ideas in physics. I loved it. Some students really didn't like it, because knowing that you were supposed to smell all the paths to get from A to B wasn't helpful for doing the homework, which was something like write down the Lagrangian for mass sliding in a hemispherical bowl or something like that. Anyway, every senior, I'll write a senior thesis at Princeton. And I guess I still had the math bug because I discovered, because I used to go to the bookstore to browse the physics and math books, a book with a very charming title by a Princeton professor, Arthur Weidman, written with Streeter, called PCT, Spin and Statistics and all that. And there was a lot in this book I didn't understand, but I read it over the summer. And of course, what was great about it to me was it was a book with rigorous mathematics about quantum field theory. The other quantum field theory books I had seen weren't like that. And so the idea that you could make quantum field theory rigorous was very appealing to me. I wound up writing a senior thesis with Arthur Weidman. He was a very approachable and kind man. Looking back, I don't know how he was so patient with me. I took a lot of his time. I had sort of a sense of entitlement. Whenever he was in his office, I'd barge in and start asking questions, but he had a great gift for making me feel like he was always glad to see me. He gave me a problem which was much too hard. I couldn't solve it. It didn't get solved actually for many years after, to show that a certain model field theory had spontaneous symmetry breakdown. But I learned a whole lot from him, and benefited a lot from all the time we spent together. So by this time, actually something that you might not appreciate, but which is worth mentioning, it's the early 1970s, and what I heard over and over again, including from my professors at Princeton, is that don't think about trying to be a professor of theoretical physics. There are no jobs. There aren't going to be any jobs. During the 1960s, the Sputnik era, there was a huge surge of hiring at universities in physics in particular. That was a time when science and technology were very prestigious. There was a feeling that American science and technology was going to be the key to democracy and freedom and our prosperity. And physics in particular was held in very high regard by the general public. And the space race had a lot to do with that. I don't think there's been any time since where the country seems so united behind a scientific or technological goal. But at any rate, at that time, there was all this faculty hiring. All these people hired in the 1960s, they weren't going to retire to the 1990s. Until then, there would be no jobs. And I heard this again and again, but for some reason, it didn't bother me. I can't really figure out why not. I figured, yeah, well, maybe that won't be true for me. So I wanted to go to graduate school in theoretical physics. And at that time, it was my view, not maybe inaccurate actually, that the most interesting theoretical particle physics was happening at Princeton and Harvard. I'd already been at Princeton, so I thought I should go to Harvard, and I did. And the part of the attraction of Harvard was that as an undergraduate, I started reading physics papers, partly because of my senior thesis, and I was very taken by the papers of Sidney Coleman, who had a wonderful style. He had great clarity and great skill as a writer, and he would give explanations that were crystal clear, but sometimes were surprising. He would explain things in ways that you wouldn't think of yourself. So I was very impressed by that. And of course, I knew of some of the other Harvard faculty, in particular, Steven Weinberg, but I envisioned that I'd go to Harvard and work with Sidney Coleman. So at that time, I think I saw Howard Georgia in the audience, unless it was an imposter. At that time, Howard was a junior faculty at Harvard, and students flocked to him because he's such a supportive mentor and had lots of great suggestions. Well, he was very approachable. Sidney also had a lot of students, but I found him very intimidating. I was a pretty shy person, and these great professors, I was afraid of them, actually, not so much of Howard because he was so nice. But for Sidney and Steve, sure. Sidney did have a lot of students because he could give such great explanations off the cuff on just about every topic. But he once said, I recall, I have graduate students like a dog has fleas. And of course, he meant that to be funny. And actually, I did think it was pretty funny. But on the other hand, he did have a lot of students. And they used to queue up outside his office because in those days, he used to sleep all morning and come in the mid-afternoon, and everybody be queued up because they wanted a little bit of time with him. And I thought, boy, who needs that? I have to stand in line, to see my advisor. But meanwhile, because I was too shy to actually talk to them, I was reading all the papers that Sidney Coleman and Stephen Weinberg had ever written. I guess I had a lot of time for those things in those days. And as time went on, although I loved everything Sidney had written, I started to feel like I was really interested in things that Weinberg had done and was doing. And in particular, I got interested in cosmology, really because of Steve, I think. Well, it was an exciting time for particle physics in the 70s. And one aspect of that was, I was in the generation that came along a little bit too late to take part in the discovery of the standard model of particle physics. But the discovery of asymptotic freedom, which was in 1973, opened up the possibility that you could study the very early universe. Until then, it wasn't clear how to follow the history of the universe back earlier than the first second or so, because that's when the strongly interacting particles behaved in a way that nobody understood. But asymptotic freedom changed that. So it became possible to envision the history of the universe at earlier times when there was a soup of quarks and gluons, which are interacting sufficiently weakly at very high temperature because of asymptotic freedom that we kind of describe what would be going on. And then meanwhile, the idea of grand unification was quite recently developed. And so the thought that you might be able to test consequences of grand unification by studying cosmology, I thought was really exciting. Steve was interested in one aspect of that, which was the origin of the excess of matter over antimatter in the universe, and how that could be explained by the grand unified theory that would be applicable during the first 10 to the minus 35 seconds or so in the history of the universe. That's still really an open question. We don't have a quantitative explanation for why, as far as I know, for why the excess of matter over antimatter in the universe is what it's observed to be. But it was a heady time when we thought we were going to understand things like that. And I think as a result of my interest in both what Sidney was doing and what Steve was doing, I had an idea, which led to my first paper. Well, I'll come to that in a minute. I wanted to say first, though, that although I was afraid of the professors, there were amazing postdocs at Harvard at the time, and those were my real mentors, especially Michael Peskin, who was my first research collaborator, and Ed Witten, who was already apparent in the mid-70s that he was sort of on a different planet. And one of the things that was inspiring about Ed was that, you think of him now as someone who's made foundational contributions to string theory and mathematics, but he's actually a very broad physicist, and his graduate work had been on aspects of deep inelastic scattering, and he was interested in things like dark matter, in nuclear physics, and he could cover everything because of his extraordinary intellectual ability, and so that was also an inspiring thing. And the other thing that was fantastic was the other students at Harvard in the late 70s. This is a far from complete list of ones who I overlapped with and interacted with. at the time who became well-known physicists, or in some cases, a mathematician or astronomer. And so between the postdocs and the students, even though I was afraid of the faculty, at least in my first few years, I learned a tremendous amount, and some of those people became good friends. Some of them were interested in condensed matter, which I wasn't as interested in then as I later became, but I learned something about it from them. And Eddie Farhi became a good friend. He, like me in the 1990s, shifted direction from particle physics to quantum computing. So I'm sure it's the case now that your fellow students at Harvard are amazing, and that's a resource which no doubt you've all learned to take advantage of. Yeah, so about that first paper, well, I had the idea. See, I learned there was something else that I found very exciting at the time, was that there were methods from topology that were filtering into physics in the mid-70s. And I had learned about that from Sidney Coleman and from reading other things. And meanwhile, I had learned about cosmology and grand unification and started to think about how those things fit together. And so I became concerned about whether magnetic monopoles, which I knew to be a generic prediction of grand unified theories, very heavy magnetic monopoles, could be created in the very early universe, and then what would happen to them? Would they annihilate and disappear? Would they stick around? And as I thought about that more, I began to feel that it was a really serious issue for cosmology. If we wanted to believe that the history of the universe went back early enough for monopoles to be created, you had to worry about how many would be created and how many would still be around. I'm getting a little worried about the time because I guess, am I already been talking for half an hour? Maybe I started a little late, I hope so. You guys are still out there, right? And so this was interesting. So I talked to Steve about this. By that time, he was my advisor. He never actually told me to work on anything. Well, actually, that's not exactly true. But at any rate, he certainly didn't tell me to work on this. And he just didn't believe it was interesting, a little discouraging. He said, well, why should I believe in these magnetic monopoles and that they'd be produced and that you really know how to calculate how many would be left? And he was rather dismissive. And that probably would have bothered me, except that there were other people who were more supportive, including some of those postdocs I mentioned, and also Sidney Coleman. I think Howard, too, was interested in what I was doing. And so anyway, that resulted in my first paper pointing out this problem for standard cosmology, that there'd just be too many magnetic monopoles left over from the Big Bang. And I submitted it, and it was rejected. And the reports I got back, well, basically were, well, we're not really sure the calculations are right. In any case, it's not really that broadly interesting enough for physical review letters. So I'm at the end of 4 years of graduate study. I have no papers except this one preprint, which has just been rejected. It was a discouraging time. I felt kind of depressed. I remember after getting this notice that the paper had been rejected, my wife Roberta and I, we went out and bought a colored TV. Until then, we only had this little black and white set, which we used to carry around the apartment. And actually having a color TV did cheer me up a little. Well, anyway, I resubmitted the paper, and it was accepted and published. But again, something that looking back seems rather strange to me is that I then was applying for postdocs. I'm in my 5th year as a PhD student. I'm going to finish this year. And I just had the one paper. And in fact, when I was applying, it hadn't yet been published. But somehow I got good offers, including the junior fellowship at Harvard. I must have had some good recommendations. And yeah, so I decided to stay at Harvard. Why would I leave? Everything was great at Harvard. Well, without going into the details, I wound up only being a junior fellow for 1 year, and I joined the junior faculty at Harvard. Actually, before I get to that, so now I've noticed this problem for cosmology, and I was interested in thinking further about that. Somebody who did think deeply about it was Alan Guth, and by the end of 1979, he had proposed the idea of cosmic inflation, which was a very important and revolutionary contribution to cosmology. And there were, I could have pursued that. It was obvious that there were good further things to do. But by then I'd gotten excited about something else, which was the idea that we then called technicolor or hypercolor, that there were new strong interactions that hadn't yet been discovered, which were responsible for the breaking of the electroweak symmetries. And what I found really interesting about that is that it was hard to build a model which was consistent with everything we knew. And I thought that was a good thing, because it meant if we find the right model, it'll be very constrained. And, just to fit the things that we already know, the model will be very predictive and will tell us what new things we're going to discover in future colliders and so on. Well, it turned out to be so hard to make models that no one ever really succeeded. So the topic in it, well, it didn't quite completely peter out, but it was surpassed by other ideas like supersymmetry. But in 1980, I thought this was where particle physics should be heading, and so that's what I wound up writing my thesis on. I can tell you a funny story about that too. So I gave a talk about this at Harvard in early 1980, my last year in graduate school, and Steve was there, Steve Weinberg. But back then, of course, there was no internet, and so the way professors would find out about new research is they would get preprints in the mail, and Steve had the habit of gathering his mail and bringing it into the seminar room and opening it during the talk. And so it'd be rip, and he'd take out a paper and look at it, rip, and he'd spend, you never really knew whether he was listening because he was opening his mail. And then a month or two goes by, and I see Steve. He's very excited. He's just gotten a paper from Michael Peskin, my old mentor, who'd been spending a sabbatical year in France. And Peskin had results which were actually quite closely related to the ones I had described in the seminar. Steve thought, Peskin's paper was really cool. He didn't seem to realize that I had similar results. But when I reminded him, he apologized. So now, I've done two rather different things, one having to do with cosmology and topological defects, and the other having to do with these new possible interactions. And so that kind of got me started on my way in physics, and I now had this reputation for being able to do work on these rather diverse topics. Then a couple of years later, I'm still at Harvard, and another interesting development occurred. Actually, Weinberg, when I was a student, had come up with the idea, which Frank Wilczek, who's good at names, called the axion, a new type of particle that was hypothetical, but which, if it existed, would explain why the symmetries of the strong interactions are what they're observed to be. Steve was always interested in symmetries. And thinking about the cosmological implications of that turned out to be interesting. And we realized with Mark Wise, who was also a postdoc at the time, and Frank Wilczek, that if depending on the details of parameters that describe the axion, it's possible for enough axions to be produced in the early universe that they could account for the dark matter, which was then a relatively new phenomenon, that there was evidence for dark matter in galaxies and clusters of galaxies. And it was especially a new idea that it could be cold dark matter, because the first thought was that maybe it's neutrinos, which behave in a different way than very cold matter, and axions would be cold dark matter. So we were able to make this proposal in 1982 that axions could be the dark matter of the universe. Now, we we're not the only ones to realize this. There were three more or less simultaneous papers with the same observation, that the way it goes sometimes in physics, when an idea is ripe to be developed. And, that was over 40 years ago, wasn't it? And, well, no, I guess it was 40 years ago, almost exactly. And the idea was, people paid attention, but it's really taken off lately because the technology has finally reached the point where maybe we'll be able to detect these axions if they're out there. Sometimes these things take time, right? Actually, I should give a lot of credit to Pierre Sakivi, who was one of the ones who also proposed the idea that there were a lot of axions left over from the Big Bang. He really took it seriously. How would we detect them if they're out there? And he had ideas about that, which he continued to pursue for a long time, and he's still actively involved in that. And that's a really important impact that he's had. Okay, well, all right. So I wound up going to Caltech. And again, it's funny how that happened kind of seamlessly. Like I said, I had become junior faculty at Harvard, but I had no illusions that I was going to get tenure at Harvard. Harvard was different then than it is now in terms of how the junior faculty, particularly in particle theory, were regarded. I think maybe 1 in 10 got promoted to tenure. Howard had been, well, of course he was promoted from junior faculty to tenure, but I knew I would not be. And so when a good opportunity came along to move to Caltech in 1983, I did. And I guess what I was trying to do with this slide is to say that in my own intellectual development, it has sometimes been pivotal to teach a course on something where I really learn it in depth by trying to explain it to a class. Actually, I taught a course on quantum chromodynamics and non-perturbative methods when I was still at Harvard, and then I repeated that at Caltech a few times. And I think I still draw on that experience now, almost 40 years later, because there were things that I really internalized in the process of teaching the subject that turned out to be very valuable years later. And another time where teaching turned out to have kind of a pivotal effect on me was when I got interested in black holes, and in particular what happens to information that falls into black holes around the late 1980s. And I taught a course about that. And as a result of which I understood why black holes emit radiation. And that's another thing that I continue to reap the benefits from for many years after. Yeah, so yes, you may realize something happened to me somewhere along the way. In the 1990s, I became interested in quantum computing and quantum information. Part of that was something very disappointing happened in 1993. For my generation of particle physicists, our great hope was that we would be the ones to understand how the electroweak symmetries get broken and what the physics beyond the standard model is. And the way we were going to access that phenomenology would be with a new collider, the superconducting super collider, which was already under construction in Texas. And then it got canceled in 1993. That was very disappointing. And I and a lot of others realized that meant it was going to be quite a long time before we'd be able to explore that physics. And it was discouraging. And I think that made me more receptive to learning about some new things. And around that time, I heard about the discovery by Peter Shor that quantum computers can solve, in particular, problems like factoring, which we think are too hard to solve with any classical information processing device. And that really excited me because just the idea that the problems you can solve that are practical to solve in the physical world are different than they otherwise would be because it's a quantum world, not a classical world. I thought that was one of the most interesting ideas. I'd ever heard. And so I started to pursue that. Now, it was kind of an awkward time in a way because I had a lot of students and my interests were starting to shift. And some of the students came along with me and some didn't. So for a while, I had students working on particle physics things and some condensed matter things and also quantum computing. I mean, it was okay. But it was, I didn't really, in the course of it, I'm not sure I realized this was sort of a career transition, but in a sense, it turned out to be that. I worried for a while that, sort of being an interloper in a field on which I hadn't previously worked, there was a community of people, it was a small community then, who had worked on quantum information for some time. And now, I was trying to join them. I thought, well, maybe I'll be regarded with suspicion or even antipathy. No, that didn't happen at all. It was a very welcoming community. I think it still is sociologically a great community in quantum information science. And I think people were pleased that, a particle physicist thought quantum information was interesting enough to focus his attention on it. And I got interested in particular in the issue of error correction. How are we going to make quantum computers work effectively despite the damaging effects of noise? The reason the macroscopic world seems classical is because of what we call decoherence, because of uncontrolled interactions of a quantum system with its environment. We have to somehow prevent or mitigate those interactions to make quantum computers work. And working out the theory of that in the 1990s was really fun. So this is another time that teaching was of great value to me. I taught a course on quantum information. I actually taught it for the first time in 1997. And by a year later, I had a set of lecture notes. By that time, there was an internet. And I actually knew how to use LaTeX. So I had some help, but there was a typed version of the notes this time instead of just my handwritten version, which got widely circulated because at that time, there really wasn't another good reference. What became the standard reference was a textbook by Michael Nielsen, who was a postdoc at Caltech at the time he was writing the book, and Ike Chuang. But in the late 90s, that didn't exist yet. And so I had the experience of teaching it and sort of arriving at my own way of thinking about it, which I really think deepened my understanding. And that turned out to be very valuable too. Yeah, so then something happened in the year 2000. We got an opportunity to create an institute at Caltech with a focus on theoretical quantum information science. How am I doing on time? Pretty badly. I've got to go a little faster. Well, actually, I think I'm almost done. But I never worried that much about money, partly because at Caltech, I had a lot of students, but they were supported by teaching fellowships, and we had money for postdocs from Caltech. I didn't really have to go out and raise it myself. But realizing that if you raise money, you can do things you couldn't otherwise do was something it took me about 20 years to catch on to. But anyway, we proposed to the National Science Foundation, which was just starting to show interest in quantum information as an emerging field, to have a center initially focused on the theory of quantum computing and quantum information. So that was an exciting time because there were really great young people who were getting their degrees, entering this field, and not so many opportunities for them to continue to develop as postdocs and faculty. So we had an amazing succession of people come through. By now, actually, over the last 20 some years, I think there are 60 people who came through Caltech as postdocs working on quantum information, quantum computing, who now are leaders in the field, faculty members around the world, or in industrial laboratories doing research or national labs. And that's something I'm really proud of. And then in 2011, we had an opportunity to expand that from just Theory Institute to a broader one. It's a Physics Frontier Center supported by the National Science Foundation, which still exists. And I think this has been great for the Caltech community to have all the students and postdocs feel like they're part of a larger activity, and to take advantage of the opportunities to interact with people doing experiment and theory in kind of a broader context. So, from the beginning, I thought quantum information, and, I should say, my particle physics colleagues wondered what had happened to me in the mid-90s. Why am I doing this quantum computing stuff? It didn't seem very fundamental. It seemed more like engineering. And of course, I, like many of us in the particle physics community, had gone into high energy physics because I was interested in the most fundamental questions about physics, and the nature and origin of the interactions and matter that exists in the universe, as well as what happened in the Big Bang and the origin of the universe. And so now I'm doing this stuff which to many people looks more like applied science, but I never thought of it as applied science. I thought these quantum information ideas are really giving us new ways to think about quantum physics, and that's going to be beneficial broadly. It's going to affect everything. It's going to affect how we understand matter. It's going to affect how we understand quantum gravity. And it's going to give rise to a technology that would have practical benefit for the world eventually. But probably, and I'm looking at it, I wrote this in the late 90s. That's decades away, probably. But, as I said here, but these ideas are going to help us understand in new ways strongly coupled dynamics in many particle systems, quantum field theory, and quantum gravity. And I think to some degree that has happened and is continuing to happen. So one of the things we realize is that if you want to think about phases of quantum matter, thinking about them from the point of view of quantum entanglement, correlations among the particles, which are illuminated by ideas from quantum computing, turns out to be very powerful. That there are different phases of matter which you can distinguish, not because of the Hamiltonians from which they arise, but because of the properties of the matter itself, and in particular, the structure of the long-range entanglement that it has. And we also realize that ideas like quantum error correction, which were developed to solve the practical problem of how do we make quantum computers work at scale despite the damaging effects of noise, that was helpful for thinking about black holes and how information gets out of black holes and how space-time is encoded and so forth. I skipped this one. Yeah, I think I want to leave time for questions, so maybe I'll skip over this too. Well, maybe I won't. So, what started to happen, and maybe 5 years ago, a little longer, which surprised me. Well, there are two things I would say that if you had asked me in the 90s, I would regard as surprising about later developments. One was that this idea that quantum information and entanglement and quantum error correction and so on is important for understanding quantum gravity, that really took off kind of suddenly. And now you can go to a meeting where people are talking about quantum gravity, and you'll hear words, concepts like quantum entanglement, quantum error correction, quantum complexity, which come from the quantum computing world, which turn out to be very valuable. And the other thing that surprised me was that, although I knew it would happen eventually, the surge in interest in quantum computing from industry seemed very sudden. And the level of investment, the number of companies, there are hundreds of them now, hundreds of startup companies developing either quantum hardware for computing or algorithms or software. And it sometimes concerns me that there are expectations about the timescale for quantum computing to confer a broadly beneficial impact on humanity are not fully realistic. So nowadays, I have to take a rather carefully balanced position. Quantum computing is exciting, it's advancing, it's enabling us to do things we couldn't do before. It's a tool for scientific discovery. When is it going to broadly benefit humanity? I don't know. That could still be a ways off. Where we see the potential benefit most clearly at present is applications to developing new materials and in chemistry and so on. But those might require much bigger quantum computing systems than we're going to be able to build for a while. But I think we're at the stage now where quantum technology really is enabling us to explore physics in new ways we never could before. And it's exciting from that point of view. I'll skip over this too. I guess the point here was just that sometimes things take a long time to be appreciated. So, in the early days, 20 years ago, thinking about quantum error correction wasn't that crowded a field, and you could, propose new ideas, which maybe were beyond what was then experimentally feasible. But eventually the technology caught up. So some of the ideas that we proposed back 20 years ago are becoming very experimentally relevant now, and sometimes it goes that way. And I think it's an important thing to think about now when there's all this industrial activity and companies, including not just the startups, but big companies like IBM and Google and Amazon are trying to build quantum computers. What's the role for the universities? Well, it's to look further ahead, to come up with new concepts and proposals, which might not be feasible with the technology we have now, but in 20 years ago are going to change the way things develop, and can also have the potential to impact, the way we explore physics, potentially before they have broader practical impact. And I'm pretty worried about the time, so let me just sum up. So how did I get here? I've had a career in physics going back to the 1970s. I feel like I always followed my curiosity. I worked on what I thought was most interesting. It's a real hard thing when you're a scientist to decide what to work on. And there are a lot of considerations that go into that. You want it to be something that if you can make progress, that'll have some impact, it'll inch science forward. But you also want it to be a problem which is, reasonably well matched to what you're good at, to your particular skill set. But you also want it to be something you're excited about. If you're not excited and you're not having fun, then, well, first of all, what's the point if you're not having fun? But also, it's much easier to move things forward if you're really excited about what you're doing. So I've tried to do that. I think, I do not have particularly strong technical skills compared to some of my colleagues in theoretical physics. So I think sometimes where I've been able to contribute is because I've acquired, sometimes it, to be honest, not such deep knowledge, but I have fairly broad knowledge about a lot of things. And so I can see connections between different things. So, so early on, I could connect cosmology and topological defects and phase transitions. And later I saw connections between quantum information theory and black holes. I think that's a valuable thing to realize, that if you have some knowledge of two different things, where there might be others who know the first thing more deeply than you do, or the second thing more deeply, but because you have sufficient knowledge of both, you can see how they fit together more clearly. I've been very lucky with the collaborators I've had, and most of those collaborations just sort of arose spontaneously. But looking back, I can see that by working with the right people, I was able to do things with them that I couldn't have hoped to do on my own. And I've always had, as a professor, lots of students and postdocs in my group, and as well as supportive faculty colleagues. And that's also, you know, those people have taught me more than I've taught them. And that's been an important part of what's made my scientific career fulfilling. I've been at a place where I feel that science is very well supported at Caltech. And then I've been very lucky. So I can't give you advice. Everybody's got to figure out their own path. We're all different. But for me, you know, on any given day, thinking about whatever I found most intellectually engaging, what I was most curious about, seemed to work out. Okay, so I hope you're still there. And I'll stop the share. I'm sorry that took longer than I anticipated, but I hope we have time for questions.